configurations that you learned how to write in the last video have a lot of connections to the organization of the periodic table. And in this video, I'm going to show you how to actually use the periodic table as a shortcut to help you write electron configurations more quickly and more easily. As a reminder, in the last video, you learned how to write electron configurations using these orbital filling diagrams. And so we started always at the bottom and filled in each of these boxes with arrows representing our electrons, making sure to fill in each box and each sublevel before we moved on to the next level, to a higher energy level. And then our electron configurations would be the text way of sort of abbreviating this information. So this actually represents lithium. I filled in 3 arrows, so that corresponds to 3 electrons, and that matches a neutral atom of lithium with atomic number 3. And the electron configuration for this, just to abbreviate everywhere I put in one of those arrows, would be 1s2, 2s1. And the big numbers in front represent the energy levels, the principal energy levels where you'll find those electrons. The letters again represent your sublevels or the shapes of those particular orbitals, and the exponents are actually the number of electrons in those specific sublevels for that particular atom. Now, if this were a face-to-face class, I would have students practice doing these orbital filling diagrams and writing the electron configurations by breaking everybody up into small groups and then assigning each small group a column of elements on the periodic table. And students would have to actually draw the orbital filling diagram for each of the elements and then write out the electron configuration for the elements in that particular column. And I do this so that we can sort of collate all that data, bring it back together, and start looking at patterns that develop between the electron configurations for those elements and their position on the periodic table. So I'm just going to walk you guys through that, and we'll do it together. But I strongly encourage you to print out a copy of those orbital filling diagrams and practice this on your own and just confirm these electron configurations that I'm going to put up here, just to make sure that you've got those orbital filling diagrams and how to fill them. You've got that down. All right, so we are going to start with the first column on the periodic table, column number 1. And the very first element right at the top there is hydrogen. So that's atomic number 1. That's pretty simple. Atomic number 1 means the neutral atom only has 1 electron. It has to start at the bottom at that 1s1. So what I'm going to do, this is the full electron configuration for hydrogen, 1s1. And we're just going to take that electron configuration and put it into the spot for hydrogen in the column, that particular column on the periodic table. And then we're going to move down the column to the next element. So that's lithium. And we just did that orbital filling diagram and electron configuration and found that it ended with 2s1. Now, in this one, it's a little bit large to try to write that full electron configuration into the space for lithium. So what I'm going to do to make this a little simpler, we're just going to take that last portion of it, that last sublevel being filled, and put it into the space that lithium occupies. So 2s1. And we'll just keep going down. The next element is sodium. So that's 11 electrons, 11 arrows to fill in. And if you do it correctly, you will find that you should end with 1 electron in the 3s sublevel. So 3s1. And again, we are just going to take that last sublevel and put it into the space for sodium on the periodic table. So that's 3s1. So this is interesting. We filled in 3 elements here, and they have all ended in S1. I'm guessing that the next element, potassium, is going to end in S1 as well. And sure enough, 19 electrons for potassium, that's its atomic number. You fill in all those 19 into that filling diagram, and you're going to find that you end with 1 electron in that 4s sublevel. And that's what we're going to put into the space for potassium right here. All right. So hopefully you're starting to see the pattern already. Everything here in column 1 ends with 1 electron in the s sublevel. There's even a pattern, though, related to the row and that principal energy level, that big number in front for each of these endings, right? They're always ending for the first row, the first element ends, one and only electron, is in that 1s sublevel. The next row, lithium in row 2, its final electron goes into the 2s sublevel. And sodium in row 3 of the periodic table is 3s, potassium is 4s, and I'm guessing that the next element, rubidium, is going to end with 5s1. And sure enough, it does. So this was a little bit longer of an electron configuration, right? So the ending actually, for me, when I wrote it here, came down on the next line. But that's what I'm going to take and put into the spot for rubidium. And we'll keep going. The next element is cesium. So that is atomic number 55. And just as you might have guessed, it's going to end with 6s1. So we'll put it right there for cesium. And last but not least will be francium. Francium has 87 electrons. Now, that's going to be a really long electron configuration, but I can guarantee you that the ending is going to match this pattern. It's going to be an S1, and since it's the 7th row, it's going to be 7S1. And sure enough, we end, our 87th electron for francium has to go into that 7s orbital, 7s1. Now let's see what this pattern looks like for the second column on the periodic table. All right, so the element that I have at the top of this block here is actually beryllium with atomic number 4. When you fill in the orbital filling diagram for that, you'll find that the 4th electron, the last one, will be the second one in that 2s block. So we're just going to take that and put it into the space for beryllium. So it's 2s2. Same energy level, principal energy level, as the lithium next to it. Same sublevel being filled, 2s. We've just got one extra electron. We went from 2s1 to 2s2. The next element is magnesium in the second column. And as you might have been able to guess at this point, that is going to continue the pattern that we see. It's going to be 3s2. And we can keep going. Calcium is atomic number 20. It's the next one down. It ends in 4s2. And as we keep going, the next one is strontium. Strontium is going to end in 5s2. Barium is going to end in 6s2. And radium is going to end in 7s2. Now, you may be wondering, what happened to 1s2? Where did that one go? Well, it turns out that 1s2 corresponds to 2 electrons, or atomic number 2, and that's helium. So helium, of course, is located way over here. And that's where our 1s2 ends up. Now, helium is actually over on top of that column because it's a noble gas. And in terms of reactivity, it fits with all of the noble gases. It also turns out that it fits with some of the other patterns that we're going to see in terms of valence electrons associated with those electron configurations. So that's another topic we're going to deal with in this particular video. But in terms of the pattern for column filling, you just have to remember that the 1s2 actually corresponds to helium at the other end of the periodic table. All right, so let's see if this pattern holds for other columns on the periodic table. So if we were to continue across row 2, our next column that we would hit would actually be column 13. So that's where we're going to go next. And I've already filled in all of the different elements and their electron configurations for column 13. And you'll notice that the pattern does hold. We're out of the S's in terms of that last sublevel being filled, and we've moved into the P's. So that's the P sublevel. Oops, I just did the wrong one for that one. It's not the end of the electron configuration for indium. This is the end, 5p1, and this is 6p1. All right, so if we take each one of those ending sublevels, we're going to see, well, they all match up and they fit. We're just starting that p sublevel and putting the first electron in there. But we've got the same pattern in terms of all ending with the same number of electrons in that sublevel. We also see the same relationship to row number and that principal energy level. The second row is where we have our first p sublevel actually showing up. The second energy level is where we actually have that first p sublevel available, and we see that we now have space for it in the periodic table in the second row. And we also see that each of those rows, the third row, the fourth row, the fifth row, we're matching in terms of that principal energy level with the actual row number. And just to show you that this pattern continues across, here's the column 14, all of the different elements that you'll find in column 14, and the last sublevel being filled from each and every one of them in their spot on the periodic table over here outlined in blue. So we're one column over from the P1 column, and that means that we now have 2 electrons in that P sublevel. But again, you'll see that the principal energy level for each of those p sublevels corresponds to the row number for that element on the periodic table. All right, so I've gone ahead and filled in the rest of the elements for columns 15, 16, 17, and 18. And I haven't bothered to write out the electron configurations or do the orbital filling diagrams because now I can see the pattern and I don't need to write them out anymore. I know what the last sublevel is going to be for each of these. As we go across a row on the periodic table, all we're doing is increasing the number of electrons in that last sublevel. So we go from 2p1, 2p2, p3, 2p4, 2p5 to 2p6. And as we go down a column on the periodic table, we are simply increasing the principal energy level that that electron actually goes into for that p sublevel. So from the second to the third to the fourth to the fifth and sixth. And that principal energy level actually matches the row number for that element on the periodic table. And there's 2 major takeaways for this. First of all, the column that an element is located in will indicate the last sublevel being filled and the number of electrons in that sublevel. And second, the row that an element is located in will indicate its highest energy level for the s and p electrons. Now you may be asking, what about those d and f sublevels? Well, there's some large blocks here that we haven't filled in. So let's see what those look like. So it turns out that if you write the electron configurations for the elements in the transition metal section, which is the central portion of the periodic table, all of those last electrons go into D sublevels. Those are the last sublevels being filled. And in the same way, if you look at the elements in the lanthanide and actinide series, those are the 2 rows that are kind of pulled out from the periodic table and put down at the bottom. All of their last electrons are going into F sublevels. And so we actually talk about these as the D and F orbital blocks, these particular sections as orbital blocks of the periodic table. And you see the same idea associated with those columns that we already identified with the S and Ps. These are what we call the S orbital block here in red, and the P in this kind of lighter lilac color. So this is a really nice pattern that kind of fits some natural division lines that you see in the organization of the periodic table. We had already separated out that middle section. That lower section is the transition metals and the lanthanide and actinide series. And it turns out that these, they're separated out for their unique properties and similar properties to each other, to all the elements within there. Turns out that they also have a lot of similarities in terms of their electron configurations. In particular, those last sublevels being filled. And we see the same basic idea with the S's and the P's, those blocks on the periodic table. Those, at the beginning of the semester, we also talked about as representing the representative elements. And it turns out that their very characteristic properties associated with each of those columns that they reside in corresponds with their electron configurations. In particular, that last sublevel being filled. All right, now I want to point out one interesting feature associated with these D and F blocks before I actually move on. Now for the S and P blocks, the principal energy level corresponds to the actual row number for the periodic table. So this is 2, 3, 4, 5, 6, and 7. But you'll notice that over here, when we enter into the transition metals, that D sublevel is actually from the principal energy level below the row number. And that's a consistent pattern for all of those D sublevel rows. And you'll see that it's just one to kind of remember as you set up your organization and you look at a periodic table, that the D sublevels are always one row or principal energy level below whatever the row number is. And you'll see the same pattern for the Fs. They're just two principal energy levels below whatever row number that they're actually associated with. So this 4F row is actually supposed to be taken out of the 6th row of the periodic table. If we split apart the table and put it right in there, that's where it would line up, is in the 6th row. And the 5F would line up in the 7th row of the periodic table. So this particular pattern does just reflect that order of filling that we see for the D and F orbitals when we look at our orbital filling diagrams. So this is a larger orbital filling diagram that shows the F sublevels in addition to the D sublevels. And I just put it in here to remind you that we fill from the bottom up. And you have to fill in the sublevels lower in energy before you move to the next one. And it does turn out for the Ds and the Fs that the S sublevels that actually occur at a higher principal energy level come lower in energy or below the Ds. So for example, for my 3D sublevel, which is right here, just below it in terms of energy is the 4s. And when I'm actually filling in an orbital filling diagram, I have to start at the 4s. I have to completely fill that before I can move to the 3D. And that just matches the pattern that we see on the periodic table. As you move across the 4th row, you have to fill in the 4s block before you start getting into the 3D, your transition metals. And just remember that this is just a function of the shape of those orbitals and the way that they ultimately overlap, and the shape of the s orbitals, particularly at those higher energy levels, is such that the electrons actually are able to just get a little bit closer to the nucleus, and that lowers their energy relative to the Ds and the Fs. And we see the same pattern for the F sublevels. Notice that this is my 4F up here. And the sublevel that's right below it on the periodic, not on the periodic table, on the orbital filling diagram is the 6s. So you're going to have to fill the 6s before you can start filling the 4f. And that just fits that pattern that we see for the lanthanide and actinide series. Now, once you know this pattern to the periodic table, these sublevel blocks, you can actually write your electron configurations based just upon the position of the element on the periodic table. We don't need those orbital filling diagrams anymore. So I'm going to go through a few examples of being able to use the periodic table to write your electron configurations. And I'm going to do it with this particular setup so that it's easy to see which block I'm actually going through. What you can do for your own periodic tables, though, is make sure that you actually outline or color in where each of these particular blocks are located, so that you'll know as we read the periodic table what blocks you're actually traveling through. So we'll do several examples, and we're going to start with one you've already seen, and that's lithium. So you already know that this is atomic number 3, and that means 3 electrons. Now, to use the periodic table to write its electron configuration, what we're going to do is actually find the location of lithium. So I know it's not actually listed here, but I know it's right here. That's its location. And this is going to tell us where to end our electron configuration. But we're going to write the electron configuration from the beginning. And to do this, we're essentially just going to read the periodic table like you would read a page in a book. When you're reading a page in a book, you always start at the upper left-hand corner, and you read across each line from left to right. And that's exactly what we're going to do here to write the electron configuration. We always start at the beginning with the first row. And we basically go across each row and fill in, as we go across each row, whatever sublevel is being filled in the principal energy level. So if we start with the first row, we start with 1s. Now, I am going to just keep reading across that row. I go from 1s1 here to 1s2 here, and that means I have filled the S block. And I keep going. Once I fill that row, I go to the next row until I hit the element that I want to write the electron configuration for. So in the next row, there's lithium right away. It's that first element in the second row. It corresponds to the 2s. And since it's the first element, it's 2s1. And that's my electron configuration for lithium. Okay, so let's start with another element. Let's write the electron configuration for carbon. Now, carbon is atomic number 6. You can look that up on your own periodic table, but I know, since I don't have the elements listed individually here, I know that that's actually located right here. It's the first element in column 14. And so that is the block that I am trying to get to, that I've just circled in red. That represents carbon space. And in order to write its electron configuration, I'm going to start at the beginning. We always start in the upper left, and we work our way across each row, just writing the electron configuration for the sublevels that we pass through until we reach that final block that we want. So for the first row, we start with 1s, and we work our way completely across that first row. There's 2 elements there, so that's 1s2. Once we finish that first row, we then travel down to the second row, and we're going to start with 2s. I travel through both of the blocks of the both of the elements on the 2s block, so that actually allows me to fill that in as 2s2. And then I'm just going to continue across the second row. And just remember that the second row, right, we just skip that large section and go all the way over. The next element in the second row is actually in column 13. And that means that we enter into the 2p block. Now, the element that I actually want for the electron configuration is right there. It's the second element in the 2p block, and that means that it is ending with 2p2. And that's my electron configuration for carbon. All right, now let's try scandium. So scandium is actually located, let me find it here. It's atomic number 21, and it is the first element in the D block of the periodic table. So it's right there, column 3, that very first element in that column. Now again, I'm going to start at the beginning in the upper left, and we're just going to go across each row and write the principal energy level and sublevel that's being filled. So for the first row, it's 1s2, and that fills the first row completely. After we've gotten through those 2 elements, we move to the second row, and it's 2s2. And just remember, we're going all the way across. The next element on the second row enters the 2p block. And we actually have to go all the way across the p block. And I just have to fill that completely. And if you can't remember how many electrons go into the p sublevel, just count how many columns you have in the p block. So 1, 2, 3, 4, 5, 6. And then I still haven't reached the element that I want, number 21, so I have to move to the third row. So now we start with 3s, We go across that S block, those first two columns, that's 3s2. We're just going to go all the way across the third row, so we're just going to fill it in completely. We move from 3s2, we move to the 3p block, and that becomes 3p6. Okay, and then we have to start on the fourth row. So I'm going to continue down here on the second line. We're going to have 4s2, because we have to go all the way through that S block, and the element that I'm interested in is right there at the beginning of that D block. It's 3d1. Okay, let's try one last one. We're getting longer and longer, but I want you guys to see how this works. So let's look at arsenic. So arsenic is atomic number 33, and it is actually right here. So that is actually in the fourth row of the periodic table in column 15. And again, we're going to start at the beginning and just go across each of those rows, filling in with the principal energy level and the sublevel. So we start for the first row, it's 1s2. Then we move to the second row, and we go 2s2. We have to go all the way across that second row. So again, we're going to go over and skip to that 2p. So that's 2p6. And then we move to the third row, and we fill in 3s2. And then if we keep going all the way across that third row to the very end, we go into the 3p6. Then we move to the 4s, the fourth row, and we start with 4s. So that's 4s2. Then from 4s2, we move into the 3d section. And again, if you don't remember how many electrons go into that D sublevel, just count how many blocks you have to go across. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns that I had to go through in that D sublevel section. So that's 3D10. And finally, we make it into the 4p block. Okay, and my element circled in red there is 1, 2, 3 spaces over. So that's 4p3. And that is the electron configuration for arsenic. All right, now these are getting longer and longer and longer. And it gets a little exhausting to write out all of this. And so usually at this point I get asked, isn't there a shortcut, some way of abbreviating these electron configurations, particularly when you get elements with lots of electrons? Well, yes, there is. And that will be the subject of the next video. Just to briefly sum up this video, the organization of elements in the periodic table reflects their electron configurations, and the position of an element on the periodic table can be used to write its electron configuration.